In the name of Almighty God, I'm Mahsa Sankosha, and today I want to talk about fluid structure interaction or FSI. Fluid structure interaction is the mutual influence between a fluid flow and a deformable or movable solid structure. In a fluid structure interaction, the fluid forces cause the structure to deform, and this deformation in turn alters the fluid flow. This coupling is crucial for understanding phenomena like a flag waving in the wind or the flutter of an aircraft wing. And how it works. The first step is fluid forces on a structure. A fluid moving around a structure exerts forces such as pressure and thermal loads that can cause the structure to deform. The next one is the structural deformation changes fluid flow. As the structure deforms, it changes the shape of the boundary, which in turn affects how the fluid flows. The next one is called an iterative process. Because the fluid and structure affect each other, they cannot be analyzed independently. Fluid structure interaction problems require a coupled analysis that iteratively solves the fluid and structural equations until the solution converges for a given time step. An example of a fluid structure interaction. The first one is in the nature. The swimming of microorganisms, the flow of blood through arteries, and the movement of plants in the water. And in the engineering, for example, aerospace, flutter and buffeting of aircraft wings. The next one is civil engineering, vibrations and collapse of bridges under wind loads. The next one is mechanical engineering, a wind turbine blade rotating due to wind or a heat valve opening and closing. The next one is offshore, oscillating mooring cables and risers in the ocean. The next one is biomedical, the interaction of blood flow with the walls of blood vessels or the function of a heart valve. And what are the applications and analysis? The first one is simulation. Sophisticated numerical methods are needed to solve these complex multi-physics problems. Software uses techniques like the finite element method for structures and the finite volume method for fluids, often in a coupled simulation. The next one is design and optimization. Understanding fluid structure interaction is essential for designing safe and efficient structures such as aircraft, bridges, and implants. And the next one is prediction failure. Fluid structure interaction analysis can predict phenomena like control reversal in aircraft, where large structural deformations can cause a loss of control. About fluid structure interaction details. Fluid structure interaction is the interaction of some movable or deformable structure with an internal or surrounding fluid flow. Fluid structure interactions can be stable or oscillatory. In oscillatory interactions, the strain induced in the solid structure causes it to move such that the source of strain is reduced, and the structure returns to its former state only for the process to repeat. And what are the examples? Fluid structure interactions are crucial consideration in design of many engineering systems. For example, automobile, aircraft, spacecraft engines, and bridges. Failing to consider the effects of oscillatory interactions can be catastrophic, especially in the structure comprising materials susceptible to fatigue. Tomogo Narrow Bridge, 1940, the first Tacoma Narrows Bridge, is probably one of the most infamous examples of large-scale failure. Aircraft wings and turbine blades can break due to fluid structure interaction oscillations. A reed actually produces sound because the system of equations governing its dynamic has oscillatory solutions. The dynamic of reed valves used in two-stroke engines and compressors is governed by fluid structure interaction. The act of blowing a raspberry is another such example. The interaction between three biological machine components such as bearings and gears and lubricant is also an example of fluid structure interaction. The lubricant flows between the contacting solid components and causes elastic deformation in them during this process. Fluid structure interactions are also happen in moving containers where liquid oscillations due to the container motion impose substantial magnitudes of forces and moments to the container structure that affect the stability of the container transport system in a highly adverse manner. Another prominent example is the startup of a rocket engine, for example, a space shuttle main engine (SSME), where fluid structure interaction can lead to considerable on-steady-side loads on the nozzle structure. In addition to pressure-driven effects, fluid structure interaction can also have a large influence on surface temperatures on supersonic and hypersonic vehicles. Fluid structure interactions also play a major role in appropriate modeling of blood vessels act as compliance tubes that change size dynamically when there are changes to blood pressure and velocity of flow. Failure to take into account this property of blood vessels can lead to a significant overestimation of resulting wall shear stress. This effect is especially imperative to take into account when analyzing uh, this kind of vessel. It has become common practice to use computational fluid dynamics to analyze patient-specific models. The neck of an vessel is the most susceptible to change to wall shear stress, or VSS. If the vessel wall becomes weak enough, it becomes at risk of rupturing when wall stress becomes too high. Fluid structure interaction models contain an overall lower VSS compared to non-compliant models. This is significant because incorrect modeling of vessel could lead to doctor deciding to perform invasive surgery on patients who were not at a high risk of rupture. While fluid structure interaction offers better analysis, it comes at a cost of highly increased computational time. Non-compliant models have a computational time of a few hours, while fluid structure interaction models could take up to 7 days to finish running. This leads to fluid structure interaction models to be most useful for preventative measures for a vessel caught early, but unusable for emergency situations where the vessel may have already departed. And what about the analysis? Fluid structure interaction problems and multiphysics problems in general are often too complex to solve analytically, and so they have to be analyzed by means of experiments or numerical simulation. Research in the field of computational fluid dynamics and computational structural dynamics is still ongoing, but the majority of these fields enables numerical simulation of fluid structure interaction. Two main approaches exist for the simulation of fluid structure interaction. And what are the problems? Monolithic approach. The equations governing the flow and the displacement of the structure are solved simultaneously with a single solver. Partition approach, the equations governing the flow and the displacement of the structure are solved separately with two distinct solvers. The monolithic approach requires a code developed for this particular combination of physical problems, whereas the partition approach preserves software modularity because an existing fluid solver and a structural solver are coupled. Moreover, the partition approach facilitates solution of the flow equations and the structural equations with different, possibly more efficient techniques which have been developed specifically for either flow equations or structural equations. On the other hand, development of a stable and accurate coupling algorithm is required in partition simulations. In conclusion, the partition approach allows reusing existing software, which has an attractive advantage. However, stability of the coupling method needs to be taken into consideration. This is especially difficult if the mass of the moving structure is small in comparison to the mass of fluid which is displaced by the structural movement. In addition, the treatment of a mesh introduces other classification of fluid structure interaction analysis. For example, one can classify them as the conforming mesh methods and the non-conforming mesh methods. Other classifications can be mesh-based methods and meshless methods. And what about the numerical simulation? A Newton Raphson method or a different fixed point iteration can be used to solve fluid structure interaction problems. Methods based on Newton-Raphson iteration are used in both the monolithic and the partitioned approach. These methods solve the nonlinear flow equations and the structural equations in the entire fluid and solid domain with a Newton-Raphson method. The systems of linear equations within the Newton-Raphson iteration can be solved without the knowledge of the Jacobian with a matrix-free iterative method using a finite difference approximation of the Jacobian vector product, whereas Newton-Raphson methods solve the flow and structural problem for the state in the entire fluid and solid domain. It is also possible to reformulate and fluid structure interaction problem as a system with only the degrees of freedom in the interfaces position as unknowns. This domain composition condenses the error of the fluid structure interaction problem into subspace related to interface. The fluid structure interaction problem can hence be written as either a root finding problem or a fixed point problem with the interface's position as unknowns. Interface Newton-Raphson methods solve this root finding problem with Newton-Raphson iteration, for example, with an approximation of the Jacobian from a linear reduced physics model. The interface quasi-Newton method with the approximation for the inverse of the Jacobian from a least squares model coops a black box full flow solver and a structural solver by means of the information that has been gathered during the coupling iteration. This technique is based on the interface block quasi-Newton technique with an approximation for the Jacobian from least squares models which formulates the fluid structure interactions problem as a system of equation with both the interface's position and the stress distribution on the interface as unknowns. This system is solved with block quasi-Newton interaction and iterations of the Gaussian Seidel type, and the Jacobians of the flow solver and structural solver are approximated by means of least squares model. The fixed point problem can be solved with fixed point iterations, also called block Gaussian Seidel iterations, which means that the flow problem and a structural problem are solved successively until the change is smaller than the convergence criterion. However, the iterations converge slowly, if at all, especially when the interaction between the fluid and the structure is strong due to the high fluid structure density ratio or the incompressibility of the fluid. The convergence of the fixed point iterations can be stabilized and accelerated by Aitken relaxation and steepest descent relaxation, which adapt the relaxation factor in each iteration based on the previous iterations. If the interaction between the fluid and the structure is weak, only one fixed point iteration is required within each time step. These so-called staggered or loosely coupled methods don't enforce the equilibrium on the fluid structure interface within a time step, but they are suitable for the simulation of aeroelasticity with heavy and rather stiff structure. Several studies have analyzed the stability of partition algorithm for the simulation of fluid structure interaction. In numerical analysis, the Newton-Raphson method, also known simply as Newton's method named after Isaac Newton and Joseph Raphson, is a root-finding algorithm which produces successively better approximation to the roots or zeros of a real-valued function. The most basic version starts with a real-valued function f, its derivative f prime, and an initial guess it is x0 for a root of f. If f satisfies certain assumption and the initial goals uh, is closed, then x1 is equal to x0 minus f x0 divided by f prime x0. The process can be started with any arbitrary initial guess, though it will generally require fewer iterations to converge if the guess is close to one of the function's roots. The method will usually converge, and furthermore, for a root of multiplicity 1, the convergence is at least quadratic, and c, the rate of the convergence in some sufficiently small neighborhood of the root. The number of correct digits of the approximation roughly doubles with each additional step. More details can be found in appendix. Householders' methods are similar but have higher order for even faster convergence. However, the extra computations required for each step can also down the overall performance relative to Newton's method, particularly if or its derivatives are computationally expensive to evaluate. In the old Babylonian period, 19th century, the side of a square of known area could be effectively approximated, and this is conjectured to have been done using a special case of Newton's method, described algebraically below by iteratively improving an initial estimate. An equivalent method can be found in Hero of Alexandria's Metricum in the first and second century, so it's often called Heron's method. Jamshid al-Kashi used a method to solve xp minus n is equal to 0 to find the roots of n, a method that was algebraically equivalent to Newton's method, and in which a similar method was found in Trigonometria Britannica, published by Henry Briggs in 1633. His method first appeared in his 1427, and Al-Kashi's works was found on the earlier contributions of polymath al-Bruni and the mathematician Sharaf. The contribution of the Al-Kashi remained largely unknown to the Western scientific community for centuries, until the work of Francis Witte, and in the 16th century, researcher discovered a technique similar to Cauchy in the context of solving scalar polynomial equations of degree 6, the method that laid the groundwork for what is now the modern Newton's method, which would be developed by Joseph Raphson and Thomas Simpson. First appeared in Isaac Newton's work in the analysis per equations numerical infinites. And the researcher translated and published a method of fluxions in 1736 by John Coulson. However, while Newton gave the basic idea, his method differs from the modern method given above. He applied the method only to a polynomial, starting with an initial root estimate and extracting a sequence of error corrections. He used each correction to rewrite the polynomial in terms of the remaining error, and then solved for a new correction of neglecting a higher degrees term. He didn't explicitly connect the method with the derivatives of or present a general formula. Newton applied this method to both numerical and algebraic problems, producing Taylor series in the latter's case. Despite this, in the latter second and the third editions of Newton's he did apply his method in an iterative manner to a non-polynomial equation, specifically Kepler's equation, which were the first published use of Newton's method in this form by him. Newton may have derived his method from a similar, less precise method by mathematician Witte. However, the two methods are not the same. The essence of Witte's own method can be found in the work of the mathematician and the Japanese mathematicians Kuo used a form of Newton's method in the 1680 to solve single variable equations, though the connection with the calculus was missing. Newton's method was first published in 1685 and the Raphson published a simplified description in Analysis Equationum Universal. Raphson also applied the method only to polynomial, but he avoided Newton's tedious rewriting process by extracting each successive correction from the original polynomial. This allowed him to derive a reusable iterative expression for each problem. Finally, in 1740, Simpson described Newton's method as an iterative method for solving general nonlinear equations using calculus, essentially giving the description above in the same publication. Simpson also gives the generalization to system of two equations and notes that Newton's method can be used for solving optimization problems by setting the gradient to zero. The Newton-Fourier imaginary problem was the first to notice the difficulties in generalizing Newton's method to complex roots of polynomials with degree greater than 2 and complex initial values. This opened the way to a study of the theory of iterations of rational functions. And what about the practical considerations? Newton's method is a powerful technique if the derivative of the function at the root is non-zero. Then the convergence is at least quadratic. As the method converges on the root, the difference between the root and the approximation is squared. The number of accurate digits roughly doubles at each step. However, there are some difficulties with the method. And what about the difficulty in calculating the derivative of function? Newton's method requires that the derivative can be calculated directly. An analytical expression for the derivative may not be easily obtainable or could be expensive to evaluate. In these situations, it may be appropriate to approximate the derivative by using the slope of a line through two nearby points on the function. Using this approximation would result in something like the second method, whose convergence is slower than that of Newton's method. And what about the failures of method to converge to the root? It is important to review the proof of quadratic convergence of Newton's method before implementing it. Specifically, one should review the assumption made in the proof. For situations where the method fails to converge, it is because the assumption made in this proof are not met. For example, in some cases, if the first derivative is not well behaved in the neighborhood of a particular root, then it is possible that Newton's method will fail to converge no matter where the initialization is set. In some cases, Newton's method can be stabilized by using successive over-relaxation, or the speed of convergence can be increased by using the same method. In a robust implementation of Newton's method, it is common to place limits on the number of iterations, bound the solution to an interval known to contain the root, and combine the method with a more robust root finding method. And what about the S convergence for roots of multiplicity greater than 1? If the root being sought has a multiplicity greater than 1, the convergence rate is merely linear. Errors reduced by a constant factor at each step, unless special steps are taken. When there are two or more roots that are close together, then it may take many iterations before the iterates get close enough to the one. And here you can see the capsule simulation for fluid structure iteration. And you can see that I have used laminar flow and moving mesh because this mesh must be moved based on the pressure that has been tolerated. And the next one is solid mechanics for measuring pressure and stress. And this deformable mesh and geometry is because of this multiple physics, that you can see that deformable mesh and geometry. And there is a parameter here. The u is the is assumed to be inlet mean velocity as a steady state, and h is the channel height. And this is a mesh, and you can see the material, the first and second material. First one is fluid, and you can detect from the dynamic viscosity it is something such as water. And this is the solid structure because you can see that we have a hardness in material, which you can see that how much the Young module is up. It is about 2e power to 5 pascal, and the density is near to a steel. And also Poisson ratio is 0.33, which indicates how much the strain from horizontal to vertical. But the first material, as you can see, is a fluid that you can see the blue one, and it's very near to the water because of dynamic viscosity, Pascal multiplied by second. We have a moving mesh and deformable domain, and a stiffness factor here. And the next physical module is laminar flow with a pressure of 1 atmosphere, and the solid mechanics. And now you can see the velocity, how much this fluid can be changed, the direction and the convergence and the pressure. stress based on Newton per square meter, moving mesh, and the last one is deformable mesh and geometry. Now there is a plot for mesh velocity based on time because the study we have used is time dependent, is about 4 seconds, and there is a based on millimeter how much this has been changed, and the time dependent is based between 0 and 4. You can see we have two range, one is between 1 and 4. This is the 4 second. Thank you so much for watching my tutorial video until the end, and also you can download this fluid structure interaction from my github.com/masterscript.